Then I'm going to move the cups around, I'm going to stop, and then I'm going to ask you which cup I poured the water into, kind of a version of the shell game. So I'll go pretty slow at first.
If y'all can't see, feel free to move out.
Yeah, you can
Yeah,
move up.
please bring your chairs up.
certainly have
Pour some
over
water into the middle cup. So which cup's water in? Okay, let's see if it is. All right, good job, nothing to it. I'm gonna go a lot faster this time, so the water's in the cup on your left. So here we go. Are you sure?
Yes.
That was pretty fast. That was freshman speed. I'm gonna slow it down to junior speed. All right, so watch a little bit more carefully this time. I'm gonna pour some water into the cup on your left. I'll move the cups at junior speed. Are you sure?
Yeah.
Still too fast. I'm going to slow this down so anybody can get this. I'm going to slow it down to senior speed. And I'll talk a little bit slower too, so any seniors here can pick up on it. I'm going to pour water into the cup on your left. Now, I'll move the cups at senior speed. Here we go. These cups of water in. All right, this is it's a really fun experiment that you can do at home, and I really like this one a lot. All the water is in the cup on your left, and the bottom of it had a small amount of powdered polymer, a very hydrophilic polymer called sodium polyacrylate. Sodium polyacrylate will absorb about 500 times its mass in water. So take your time and shake it, and then set it. There's some things to take note about it here. Molecules are moving, solid, liquid, or gas, they're moving. And so it should make sense to you that in order to get a chemical reaction, molecules must collide with each other. They can't text each other, they're not telepathic, all right? They don't have eyes, they can't see each other. They literally got to hit each other. In that film canister, they're hitting each other very, very frequently. But now what we're going to do is we're going to do a reaction in the gas phase. And what we have in there is the hydrogen and oxygen in a stoichiometric ratio there. They are definitely hitting each other, not nearly as frequently as in the film canister, but they are. If you could piggyback on one of those molecules in there, it's hitting one of its buddies about 1 billion times every second. So they're definitely hitting each other, but they're not hitting each other hard enough to do anything. But we could leave it sit there for 100 years, not going to do anything. But Nick's going to change that. He's going to apply a match to it. And what the match is going to do, it's going to create some free radicals. So it's going to have some odd electron species. When they collide with somebody, they react first time, every time. Generates energy, which creates more free radicals, which generates more energy. And what you get is you get a chain reaction. It's going to react very, very fast. It's going to shove all the air out of the way. It's going to create a shock wave that's going to explode. So I need you to put those on. Okay. Now, this is what he's going to do. When I give you the signal, I'd like you to light the match. Once I see the match is lit, you're going to see me take the stopper off the bottle. You're going to watch me cover my ears, and then you're going to hold the lit match horizontally across the lip of the bottle and try not to let go. Now, what I want you guys to do, I want you to watch the lip of the bottle carefully, and I'll talk about what this thing looks like. But you don't want to blink or you'll miss it. It's very, very rapid. reaction. You might want to cover your ears, it's very loud. Right?
Nah.
Okay, so again, when I give you a signal green light, I remove, I cover, hold. All right, go ahead and light it. Wait till I cover. Go ahead. And it got the match out of its hand. All right, now, liquid nitrogen in the beaker, and I want you to describe to them what it looks like it's doing.
Looks like it's boiling.
Yes, because it is. You know, most of us, of course, the only thing we've ever seen boil in our lives is water. And water boils at 212 above 0 Fahrenheit. This boils at 320 below 0 Fahrenheit. Looks hot, it definitely isn't. It's sucking energy out of the tabletop and the air in order to make it boil. And Tori, I want you to trust me on this. Convince yourself that the gas coming off really isn't hot. Once you take your hand, I want you to stick it in the beaker, just don't touch the liquid. Even if she does, she won't do it for very long. Okay, good. And you can definitely feel that it's cold. What's the smoke coming out? Anybody know? It's not nitrogen. We know nitrogen's colorless because 80% of the air is nitrogen.
Water.
It's water. And so if there's a humidity in the air, it's cold enough to cause it to condense, so that the smoke that you see is just water vapor. We're going to do a couple of experiments to show everybody how cold this is. All right, we're going to take the balloon. And this is a really important aspect of thinking like a molecule here. So we've got a balloon, and we know the molecules are banging around and they're trying to get out. I'm going to have you grab this, and I'm going to help you with this experiment. If you haven't done before, it's creepy, but you're not going to get hurt or anything. And I'm going to take your hand and we're going to lower it into the beaker. I want you guys to think about what's going to happen. So the molecules are going to start to slow down as they get cooler, slowing down so they're not hitting the balloon as hard anymore, so you're not getting as much pressure. So the outside pressure now is causing the balloon to collapse because the molecules are not moving very fast. But if we take it out, they'll start to move faster and faster and faster, and it'll just come back to normal. All right? We'll lower it into there again. I'd like you to just let go of it. Now, this should give you a physical chemist's perception of temperature. All temperature is, it's a measure of molecular motion, right? On a cold day, molecules are moving slower, not hitting you as hard, not giving you as much energy. You perceive that as being cold. Hot day like now, they're moving a lot faster on average, and so you perceive that as being warm. Now, one thing you got to be careful about when you're designing, like the shuttle main engines, when you have these cryogenic systems, are what you use for gaskets, what you use for sealants on things. A latex rubber is not a very good choice. All right, you'll see why. Because it's pretty brittle at those temperatures. So you got to really think about what it is that you're going to use when you put all the materials together, certainly from a chemistry perspective. I'd like you to pick somebody to help you. Jordan.
Oh, great. What am I doing now?
We're going to do this one just because it's fun, all right? And you're going to need, both of you are going to need your hands here. And Jordan, can I just stand over there? Right there. And I need you to put these on. All right. And Tori, if you feel that, nice and soft. Carnation petals nice and soft, almost all water. You know, you touch your skin, soft for the same reason, almost all water. You're going to see what it does to the water in here at 320 below for 3 seconds. And so I want you to hold it like that. You and I, we're going to hold it into there for 3 seconds. We're going to take it out. We're going to shake it off. We're going to hold it over the paper towel. And when I tell you to clap it, Jordan, right on the flower, clap it, and then let it. Feel it one more time so I can feel like that anymore. 1 1,000. 2 1,000, 3 1,000. Clap it. And of course, the consistency is a lot different now, so it's really hard as a rock. It feels like glass because it's so thin and everything, but nicely done, made a nice mess too. So I think they deserve an applause. They both did a nice job on this. Now, you got to ask yourself, well, why? You got to go. And I'm just going to put this here. Now, because I don't know exactly what this is going to do every single time, I'm going to light this. It's not that it's dangerous, but if you don't know what it's going to do, it's a little creepy. It may not light on the first match. It's not very sensitive at all. But I want you to watch it. has to do with the mixture and how well you pulverized it. Kind of keeping my eye on it. Usually when I reach down with the second match, it starts. I'm not going to give up. Very stubborn. No, no. Ah. Oh, there we go. There we go. All right, that's what we wanted. Notice the purple flame, that's from the potassium in there. If you're close enough, it smells like a burned marshmallow, because it is. I mean, if you were burning powdered sugar. I do know what this is going to do 100% of the time, so I am going to let you do this. Okay. And put a little bit of gunpowder there. Rather than sugar, it's using charcoal, much better fuel than sugar, like barbecuing a hot dog or something. Still uses potassium nitrate. In there's the oxidizer, and then it's got one other ingredient. It's got some sulfur in there. What the sulfur does is more evenly distributes the heat throughout the propellant grain, so it'll burn a lot faster. Now you don't want to reach down there with your hand. We're going to use a chicken stick instead. You'll see why. So what we're going to do is you're going to practice this first. I want you to hold on to it like this, and then I'm going to light the match. And once it's lit, you want to hold it so it's touching the top of the pile. Go ahead and practice.
Like that?
Yeah, just like that. So it's touching it. It's got to be touching it.
Like that.
Just like that, and then wait for something to happen. And don't worry,
Okay.
once it does it so fast, you won't have any time to move your hand. I like to light the match away from the gunpowder. Good. So
Now just touch it.
just keep it, hold it there. It takes a little while for it to transfer the heat. Don't worry about it. Honest. Okay, now trust me on this. Hold your hand open.
Yep.
It's cold. Stone cold. That's what we want. All right. You got plenty of time. A little faster than that. It'll start to smoke once it generates some heat. It's going to burst into flames. All right, so pretty nice job. I'm going to cover it. It's going to continue to burn. It's got everything that it needs in order to burn because it's got the oxidizer. So you could actually do this reaction in space just fine. I've got enough to, and he did a nice job. I think he deserves some applause on this. I'm going to put some dishwashing liquid on top of it, and that's going to capture the oxygen so they can actually see this. This is often called elephant toothpaste. You'll see why. It's a great demonstration. Now, what we could use for the catalyst, we could chop off Nicole's little finger and toss the stub in there, and that would work just fine. But what we're going to use is we're going to use some potassium iodide solution, which works even better. Now, this is what I'd like you to do, Nicole, is I'm going to hold on to this. I want you to hold this so the lip is touching that, but not pouring it yet. And then when I tell you to pour it all in there carefully but quickly, and then get your hand out of the way.
Okay.
All right, anytime you're ready. Pour it quick and move your hand. Okay. Now I want you to hold your hand over the top and you can feel the heat coming off of there. I like to close with this one because it really illustrates what you're looking for a rocket. You gotta have a chemical reaction that will produce gas. That's what's gonna make the thing move. All right, and clearly we can see quite a bit of gas coming out of there when we captured it. It's gotta be hot, right? Because it's gonna make the average velocity much higher. And she could feel the warmth coming off of there.
Yeah,
And
warm shower.
right, yeah, it really is.
Yeah.
And then the chemical reaction has to be very, very rapid. All right, can't be a slow one like the Alka-Seltzer one, much too unpredictable. And of course, a lot of the rocket chemistry, the thermodynamics is very, very well understood. The kinetics part is the really, really difficult part of it, but the thermal is very, very well understood.